Have you ever stopped to consider the sheer monumental inefficiency of our modern electrical world? We live in an age defined by the flow of electrons, yet the way we move them from one place to another is staggeringly wasteful. Every time you flip a light switch, turn on your television, or plug in your smartphone, you are tapping into a vast, unimaginably complex global web of power generation and distribution. However, this web is fundamentally flawed. When electricity leaves a power plant, whether it is a roaring coal furnace, a silent nuclear reactor, or a shimmering field of solar panels, embarks on a journey through miles and miles of metal wire, usually made of copper or aluminum. Along this journey, the electrical current encounters constant, inescapable resistance. The electrons, as they travel through the atomic lattice of the wire, constantly collide with the atoms of the metal. These collisions generate friction, and that friction generates heat. This is not a trivial loss. Globally, it is estimated that we lose anywhere from 5 to 10% of all the electricity we generate just in the process of moving it from the power plant to the consumer. Think about that for a moment. 5 to 10% of the coal we burn, the natural gas we ignite, and the nuclear material we consume is entirely wasted. It simply dissipates into the surrounding air as low-grade heat, warming up the sky for absolutely no benefit. In terms of pure economics, this represents hundreds of billions of dollars vanishing into thin air every single year. In terms of the environment, it translates to hundreds of millions of tons of unnecessary greenhouse gas emissions pumped into our fragile atmosphere, exacerbating climate change and polluting the air we breathe. We have built our entire civilization on a leaky foundation, simply accepting this massive hemorrhage of energy as a tragic but unavoidable law of nature. But what if it is not unavoidable? What if we could completely rewrite the rules of how electricity behaves? Imagine a world where resistance does not exist. A world where electrical current can flow through a wire forever, across thousands of miles, without losing even a single drop of energy to heat. This is not some speculative science fiction concept. It is a very real, very well-documented physical phenomenon. It is called superconductivity. When certain materials are subjected to incredibly specific conditions, something seemingly miraculous happens at the quantum level. The internal electrical resistance of the material drops precipitously, not just to a low level, but absolutely, exactly to zero. The electrons, which normally bounce around chaotically and lose energy, suddenly pair up in what are known as Cooper pairs. They begin to move in perfect, synchronized harmony through the atomic lattice, gliding without a single collision. If you were to take a loop of superconducting wire, introduce an electrical current, and then seal the loop, that current would continue to circulate with undiminished strength for billions of years. It is as close to perpetual motion as the laws of physics will allow. To truly understand the magnitude of this phenomenon, we have to look back at humanity's long struggle to understand the fundamental forces of nature. The roots of this journey stretch deep into antiquity. As far back as 600 BC, ancient Greek philosophers and thinkers in other early civilizations observed the curious properties of lodestones, naturally magnetized pieces of the mineral magnetite. They marveled at how these strange stones could attract bits of iron, seemingly by magic, across empty space. For millennia, this was viewed as a curiosity, a mysterious force disconnected from the everyday world. It took thousands of years of painstaking observation and deduction to slowly knit together the separate phenomena of electricity and magnetism into a single, unified theory of electromagnetism. The breakthrough that led to the discovery of superconductivity did not happen until the early 20th century. In 1911 AD, a Dutch physicist named Heike Kamerlingh Onnes was experimenting with the properties of matter at extreme cold temperatures. He had recently mastered the technique of liquefying helium, allowing him to reach temperatures just a few degrees above absolute zero's a theoretical limit where all atomic motion stops. When Onnes cooled a simple wire of solid mercury down to 4.2 degrees Kelvin, he observed something astonishing. The electrical resistance of the mercury didn't just decrease, it completely vanished. He had discovered the superconducting state, a discovery that fundamentally altered our understanding of quantum mechanics and condensed matter physics. However, there was an enormous catch, and it is a catch that has plagued physics ever since. The materials Onnes discovered, and the hundreds of superconducting materials discovered in the decades that followed, only exhibit this magical property at violently extreme cryogenic temperatures. We are talking about temperatures hundreds of degrees below freezing, environments colder than the deepest reaches of outer space. To achieve these temperatures, scientists and engineers are entirely reliant on cryogenic fluids, primarily liquid helium and liquid nitrogen. This reliance on extreme cooling is the great bottleneck of the technology. Liquid helium is notoriously difficult to handle, requires massive, complex, and highly insulated refrigeration systems, and is incredibly expensive. In fact, helium is a non-renewable resource on Earth, extracted as a byproduct of natural gas mining, and we are slowly running out of it. Because of these immense cooling requirements, superconductors have remained confined to highly specialized, well-funded, and stationary applications. You will find them creating the incredibly powerful magnetic fields inside MRI machines at major hospitals. You will find them steering protons at near the speed of light inside the Large Hadron Collider at CERN. But you will not find them in the power lines running down your street, or in the internal circuitry of your laptop, or in the motors of everyday electric cars. The cryogenic cooling infrastructure required would take up vastly more space, cost vastly more money, and consume more energy than the superconductor itself could ever hope to save. This brings us to the holy grail of modern physics, arguably the most sought-after discovery in all of materials science: the room temperature superconductor. This would be a material that exhibits zero electrical resistance, not at the frigid temperatures of liquid helium, but at everyday ambient temperatures. A material you could hold in your hand on a warm summer day, and it would still conduct electricity with absolute perfect efficiency. If such a material were to be discovered, and crucially, if it could be manufactured in a practical, usable form like flexible wires or thin films, it would trigger a technological and economic revolution on a scale not seen since the mastery of fire or the invention of the steam engine. It would be the kind of breakthrough that neatly divides human history into a before and an after. The search for this elusive material is a massive, highly competitive global endeavor. Thousands of the brightest minds on the planet are dedicating their careers to this pursuit, testing countless combinations of elements, subjecting strange ceramic compounds to immense pressures, and running complex computer simulations to predict new crystal structures. This research stretches across the globe, from the massive national laboratories in the United States and Europe, to cutting-edge research institutes in Asia, all the way to advanced university labs in Palestine, modern-day Israel, where scientists are tirelessly working to break the temperature barrier. It is a quest fraught with false alarms and dashed hopes. But the potential prize is so astronomically high that the search never slows down. To understand why this is such a transformative prospect, let us systematically explore how a room temperature superconductor would fundamentally rewrite the rules of our civilization. We must start with the most obvious and immediate application: the global power grid. As mentioned earlier, we lose 5 to 10% of all electricity in transmission. If we could replace the heavy resistive copper and aluminum wires of our high-voltage transmission lines with room temperature superconducting cables, that loss drops to zero instantly. Without building a single new power plant, without installing a single new solar panel or wind turbine, humanity would instantly gain a massive surplus of usable energy. Power plants could dial back their output, immediately reducing global greenhouse gas emissions and saving billions of dollars in fuel costs, all while delivering the exact same amount of power to consumers. But the implications for the power grid go much, much deeper than simply reclaiming lost efficiency. The current electrical grid is inherently limited by distance. Because energy is lost over distance, power generation must be relatively close to the population centers that consume it. This is why we have coal plants and nuclear reactors built near major cities. Despite the obvious environmental and safety concerns, it is also the primary reason why we have not been able to fully transition to a purely renewable energy economy. Consider solar power. There are places on Earth, like the middle of the Sahara Desert, the Mojave Desert, or the vast arid expanses of Australia, that receive an absolutely staggering amount of solar radiation year-round. Theoretically, a massive solar array built in a fraction of the Sahara could generate enough electricity to power the entire planet. But we cannot currently do that, because by the time you try to transmit that electricity from the Sahara to a bustling metropolis like London or Tokyo using conventional copper wires, almost all of the energy would be lost to heat along the way. The resistance over those thousands of miles would simply be too great. Room temperature superconducting cables completely destroy this geographical limitation. Because there is zero resistance, you can transmit electricity over 1 mile or 10,000 miles with exactly the same perfect efficiency. Suddenly, distance is no longer a factor in energy infrastructure. We could build colossal, continent-spanning solar arrays in the most sun-drenched, uninhabited deserts on Earth. We could build massive wind farms in the most turbulent, isolated stretches of the global oceans. We could then connect these massive, pristine sources of renewable energy to a truly global, interconnected superconducting grid. This global grid would solve the greatest problem facing renewable energy. The wind does not always blow, and the sun does not always shine, at least not in one specific location. But the sun is always shining somewhere on Earth, and the wind is always blowing somewhere. With a global zero-loss grid, a solar farm basking in the midday sun in North Africa could instantly and effortlessly route its surplus power to Northern Europe, where it is the middle of the night. A few hours later, as the Earth turns, solar arrays in the American Southwest could pick up the slack. The entire planet would act as a single unified energy organism, seamlessly routing clean, abundant power from where it is generated to precisely where it is needed. This single technological advancement would likely be the silver bullet that allows humanity to finally and completely transition away from fossil fuels, averting the worst catastrophes of climate change and building a truly sustainable civilization. However, moving energy perfectly is only half of the equation. We must also be able to store it. The inability to efficiently store large amounts of electricity is perhaps the weakest link in our modern technological chain. When we generate electricity, it generally has to be consumed in that exact moment. To store it for later, we currently rely heavily on chemical batteries, like the massive lithium-ion battery banks being installed to support renewable energy projects. Chemical batteries, while useful, are fundamentally flawed. They are incredibly heavy, incredibly expensive to manufacture, and they rely on the extensive mining of rare earth metals and toxic chemicals, often in geopolitical hotspots. Furthermore, batteries degrade over time. Every time you charge and discharge a chemical battery, you damage its internal chemistry slightly, reducing its overall capacity until it eventually dies and becomes hazardous electronic waste. Room temperature superconductors offer a radically different and vastly superior method of storing energy, known as a superconducting magnetic energy storage system, or SMES for short. The concept is beautifully simple, though entirely dependent on superconducting physics, because a current can flow endlessly through a superconducting loop without degrading. You can essentially trap electricity in a holding pattern. You could build enormous rings of superconducting cable, perhaps buried safely underground beneath major cities or alongside massive solar farms. During times of low demand, such as the middle of the night, you pump massive amounts of surplus electrical energy into this ring. The energy does not sit in a chemical state. It circles continuously, stored indefinitely as a powerful magnetic field. When the city wakes up and demand spikes, you simply tap into the loop and draw the electricity back out. The beauty of this system is that, unlike chemical batteries, a superconducting storage ring would have virtually zero degradation over time. You could charge and discharge it millions of times, and it would hold just as much energy on day 10,000 as it did on day 1. It requires no toxic chemicals, no massive mining operations for lithium or cobalt. Municipalities could build massive shared storage rings, banking the intense solar energy generated during summer days to seamlessly power the city through long winter nights. This would provide absolute, unshakable stability to the global power grid, completely eliminating the risk of blackouts or brownouts and rendering our current fragile, battery-dependent electrical infrastructure completely obsolete. As we revolutionize how we move and store energy, we must naturally look at how we move ourselves. The transportation sector is currently one of the largest contributors to global greenhouse gas emissions, heavily reliant on the combustion of fossil fuels. Room temperature superconductors would trigger an immediate and radical transformation across all modes of transport. Let us begin with ground transportation, specifically rail. You have likely heard of magnetic levitation or maglev trains. These incredible machines use powerful electromagnets to levitate the train cars just a few inches above a specialized track. Because there is no physical contact between the train and the track, mechanical friction is completely eliminated. This allows maglev trains to travel incredibly smoothly and at astonishing speeds, far surpassing traditional high-speed rail. Currently, maglev trains exist in only a few highly specialized locations in the world, such as the famous line in Shanghai, China, or the experimental tracks in Japan. The reason they are not everywhere is cost. The powerful magnetic fields required to levitate a heavy train are generated by superconducting magnets. Because we currently lack room temperature superconductors, the tracks or the trains themselves must be equipped with incredibly expensive, heavy, and complex liquid helium cooling systems. This makes building a vast network of maglev tracks economically unfeasible for most nations. A room temperature superconductor changes the math entirely. If the magnets do not require extreme cooling, the cost of building both the trains and the levitating tracks plummets dramatically. Magnetic levitation becomes cheap, practical, and ubiquitous. We could envision building vast continent-spanning networks of levitating high-speed rail. Because mechanical friction is almost entirely eliminated, the only limiting factor on speed is air resistance. If these trains were placed inside partially evacuated tubes, a concept often referred to as the hyperloop, they could easily travel in excess of 1,000 or even 2,000 miles per hour, rivaling or even surpassing the speed of commercial jet travel. But unlike airplanes, which burn thousands of gallons of highly refined aviation fuel and emit tons of carbon dioxide and other pollutants straight into the vulnerable upper atmosphere, these superconducting maglev trains would be entirely electric. They would draw their power directly from our newly perfected, lossless, globally interconnected, renewable energy grid. The cost of long-distance travel and global shipping would plummet to a fraction of its current cost. The world would shrink dramatically, connecting economies, cultures, and people in ways previously unimaginable, all while rapidly decarbonizing the global transport sector. This transformation would not be limited to massive public transit projects. It would deeply impact personal vehicles as well. The electric vehicle industry is currently booming, but it is heavily constrained by the limitations of chemical batteries. The batteries are the heaviest, most expensive, and most problematic component of any electric car. They dictate the vehicle's range, its charge time, and its eventual lifespan. If we successfully develop small-scale superconducting magnetic energy storage systems using room temperature materials, the chemical battery could be vastly supplemented or even replaced entirely. You could have a small, incredibly potent superconducting loop in your car, storing electricity as a magnetic field. This would weigh a fraction of a lithium-ion battery pack, cost less to manufacture at scale, and, crucially, it could be charged almost instantaneously. You wouldn't need to wait an hour at a charging station. You could dump massive amounts of current into the superconducting loop in seconds, getting back on the road immediately. Furthermore, the electric motors that drive the wheels of the car would undergo a revolution of their own. Traditional electric motors use copper coils to generate magnetic fields. These coils have resistance, which means they generate heat, which means they require heavy cooling systems and have hard limits on their torque and power output. If you build an electric motor using superconducting wire, the coils have zero resistance. They generate no waste heat whatsoever. This means you can push vastly more current through them, generating incredibly powerful magnetic fields and astonishing amounts of torque from a very small, very lightweight motor. Electric cars would become significantly lighter, which inherently makes them more efficient. They would become vastly faster, much cheaper to build, and possess ranges that vastly exceed anything on the market today. This combination of lightweight, highly efficient superconducting motors and instantaneous superconducting energy storage might even be the key to unlocking practical electric-powered aviation. Currently, batteries are simply too heavy relative to the energy they hold to make large-scale electric passenger planes viable. But a superconducting propulsion and storage system could finally drop the weight-to-power ratio low enough to see clean, silent electric jetliners crossing the skies. While the impact on energy and transportation is easy to visualize, the impact of room temperature superconductors on computing and information technology might be the most profound and far-reaching of all. We live in the information age, an era entirely dependent on our ability to process and manipulate digital data. Modern computers are marvels of engineering, but they are fundamentally limited by a very simple, very ancient enemy: heat. The beating heart of any computer, from the smartphone in your pocket to the massive servers running the internet, is the microchip. Inside these chips are billions of microscopic transistors, acting as tiny electrical switches, turning the flow of electrons on and off to process binary information. But every single time one of those billions of transistors switches states, the electrons encounter the inherent electrical resistance of the silicon and the copper wiring. And just like in a power line, that resistance generates a microscopic amount of heat. When you pack billions of these transistors onto a sliver of silicon the size of a fingernail, and you ask them to switch states billions of times every single second, those microscopic amounts of heat add up incredibly quickly. This is the primary bottleneck of modern computing. It is the reason your laptop gets hot when you play a demanding game. It is the reason computers have loud spinning fans. It is the reason why the massive data centers that power cloud computing and artificial intelligence require massive industrial-scale air conditioning systems, consuming entire percentage points of the global electricity supply just to keep their servers from melting down. More importantly, heat is the reason we cannot push processor clock speeds much faster than we currently do. If you try to run a conventional silicon chip too fast, the heat generated by the resistance will literally melt the delicate internal structures, destroying the chip entirely. We have largely hit a wall in terms of raw processor speed, forced instead to add more cores or rely on specialized, less flexible architectures to squeeze out more performance. Room temperature superconductors would absolutely shatter this limitation. Imagine if the internal wiring and the intricate connections of a microchip were constructed using a superconducting material instead of copper or gold. The electrical resistance within the chip would drop to absolute zero. No resistance means zero heat generation from the wiring. Without the barrier of heat, we could instantly crank processor clock speeds up by orders of magnitude. We could push data through the chips at blistering speeds, making our computers thousands, or perhaps even millions of times faster than they are today, all while using a mere fraction of the electrical power. The massive, energy-hungry data centers that currently dominate the technology landscape would suddenly run cold and completely silent. This leap in pure processing power would not just mean better video games or faster web browsing. It would act as a massive accelerant for every other field of human endeavor. We are currently seeing the dawn of the artificial intelligence era, but AI is heavily constrained by compute power. Training a cutting-edge large language model or a complex neural network currently takes months of continuous processing on massive multi-million-dollar supercomputers. With superconducting processors, those same AI algorithms could potentially be trained in minutes or seconds. The pace of AI development would explode, leading to rapidly superintelligent systems capable of solving problems that currently baffle humanity. Complex computer simulations that currently take years to run, such as simulating the complex folding of protein molecules to discover new drugs, modeling incredibly intricate global weather patterns to predict climate shifts, or simulating the chaotic behavior of plasma to perfect nuclear fusion reactors would become trivial tasks. We are currently bumping hard against the physical limits of Moore's law and traditional silicon-based computing. Room temperature superconductors offer a clear, elegant path to bypass those limits entirely, launching us into a new era of computational capability that borders on the unimaginable, accelerating scientific discovery in every other discipline. The medical field would also be an immediate and profound beneficiary of this technology. One of the most powerful and important diagnostic tools in all of modern medicine is magnetic resonance imaging, or MRI. An MRI machine uses incredibly strong, highly uniform magnetic fields to interact with the water molecules inside the human body, allowing doctors to peer inside tissue and bone with unparalleled clarity without using harmful ionizing radiation like X-ray. But, as we have noted previously, creating those massive, stable magnetic fields requires the use of superconducting electromagnets. And currently, those electromagnets must be cooled to near absolute zero using liquid helium. This makes MRI machines incredibly large, incredibly expensive to purchase and install, and exorbitantly expensive to operate and maintain. A typical hospital MRI requires thousands of liters of liquid helium, scarce, expensive, non-renewable resource just to keep its internal temperature stable. This high cost severely limits access to this life-saving technology. While commonplace in wealthy nations, MRI machines are scarce in developing parts of the world. And even in wealthy countries, the cost of a scan is very high. If we possessed practical room-temperature superconductors, we could build MRI machines that require absolutely zero cryogenic cooling. The massive insulated cooling jackets and the complex liquid helium pumping systems would be entirely eliminated. The machines would become vastly cheaper to manufacture, much smaller, and incredibly simple to maintain. You could easily install a highly advanced MRI machine in a small rural clinic, or even place a portable version in the back of an ambulance, allowing for immediate high-resolution scans at the site of an accident or a stroke. Furthermore, because superconducting electromagnets can generate incredibly strong fields without the bulk of cryogenic systems, the physical design of the scanners could change. We could build more open, less claustrophobic machines with dramatically increased resolution. Doctors would be able to diagnose diseases like cancer, Alzheimer's, or subtle heart defects at their earliest, most microscopic, and most treatable stages. The democratization of advanced medical imaging would lead to a profound and immediate improvement in global health outcomes, saving millions of lives and reducing healthcare costs worldwide. Finally, we must consider the strange, almost magical phenomenon of quantum locking, also known as magnetic levitation via the Meissner effect. This is perhaps the most visually striking property of a superconductor. When a material transitions into its superconducting state, it does not just lose electrical resistance, it also actively expels all magnetic fields from its interior. If you place a superconductor near a strong magnet, the magnetic field lines are forced to bend around the superconductor. This creates an incredibly strong, stable repulsion. The superconductor becomes locked in three-dimensional space relative to the magnet. It can levitate perfectly still, suspended in midair, defying gravity without any external power source or mechanical support. You can push it, spin it, or turn the magnet upside down, and the superconductor will remain locked in its precise position. Currently, this is a beautiful laboratory trick, performed with small pucks of superconducting ceramic, cooled with liquid nitrogen over a track of rare earth magnets. But with room-temperature superconductors, this effect escapes the cryogenic laboratory and enters the real world. The applications for frictionless quantum-locked bearings are staggering. Imagine industrial machinery, from massive factory turbines to the tiny moving parts inside delicate instruments built without physical contact between moving components. We could completely eliminate wear and tear caused by mechanical friction. Machinery would last vastly longer, require far less maintenance, and operate with near-perfect efficiency. We could design entirely new types of architecture and infrastructure, utilizing magnetic levitation to create structures that seem to defy gravity, or moving components that slide effortlessly without lubrication or degradation. The physical world around us would become smoother, quieter, and vastly more efficient. The discovery of a true practical room-temperature superconductor would undeniably be a watershed moment in human history. Perhaps the single most important materials discovery since humanity first learned to forge. Bronze, or smelt iron, it is one of the very few theoretical technologies that possesses the sheer scale and capability to solve multiple existential global crises simultaneously. It offers a clear, elegant, and purely technological pathway out of the impending climate catastrophe by enabling a perfect, unified, and perfectly efficient global renewable energy grid. It promises to democratize ultra-high-speed travel, shrinking the planet and reducing the environmental impact of moving goods and people. It guarantees to revolutionize the very foundations of computing, unlocking levels of artificial intelligence and scientific simulation that will propel human knowledge forward at an unprecedented rate. And it promises to expand access to life-saving advanced healthcare to every corner of the globe. Yet, as we consider this incredibly bright and transformative future, we must also soberly acknowledge the intense difficulty of the scientific quest. Despite decades of intense, well-funded effort, despite numerous false alarms and premature announcements, a practical, verifiable room temperature, ambient pressure superconductor remains frustratingly elusive. The fundamental physics governing high-temperature superconductivity are incredibly complex, and nature has proven to be profoundly stubborn on this front. But the potential rewards are so absolute, so profoundly and permanently transformative for the human species, that the search continues to attract some of the brightest and most dedicated minds on the planet. We are looking for a material that fundamentally rewrites the rules of engagement with the physical universe. We are searching for a substance that will allow humanity to finally harness and utilize energy with perfect, unyielding efficiency. If and when that day comes, when the temperature barrier is finally broken and the resistance drops to zero, the world will change faster, and more fundamentally, than we can currently possibly imagine.